students and me and maybe other teachers, maybe your parents if your parents ever went through Calc 2. This is typically considered sort of the hardest topic in Calc 2, the infinite series thing. And it feels very isolated because we do nothing. Well, improper integration is a little bit like infinite series, where we're trying to find the area of an unbounded region. It's a little bit like that. But then once we finish it, you never see it again in Calc 3, and you don't see it again until Diffie-Q. So it's really tempting to just sort of think, oh, I just have to get through infinite series and then I'll be done. You won't be done. They are going to come back. So I really advise you to try to dig in right from the start, right from this first section where it's all definitions, and it seems it's going to feel very easy actually at first, the first couple of sections. But really try to stay up on it, and it is going to come back. My son, who is a computer science major, is now seeing infinite series in 3 courses. So it does come back because it's a very practical skill that allows you to solve problems in engineering and other disciplines that are math-based. So don't just think that it's kind of like this anomaly that we just look at it for a little bit. It will come back, and it will come back because of the world. When we go out into the world, things aren't nicely packaged, and it turns out that infinite series are sort of the way that we solve a lot of differential equations in particular. So keep in mind that this is something you're going to have to build on. There are some things that we do in Calc 2 and Calc 3 that you really, are more just foundational for other things, but infinite series is something that you actually will use going forward as a thing in and of itself. Okay, so we're going to start with the definition of a sequence. So we're going to have these 2 concepts, sequence and series. When you hear sequence, you should be thinking of commas. You should be thinking of a list. So a sequence is an ordered list, okay? So it's just a big, long array, if you want to think of it that way. So it's just a big, long list, separated, and it is ordered, though. A sub 1 usually represents the first term, A sub 2 the second term, etc. A sub n represents the nth term. Now it is possible in certain situations where you don't want to start with your counting at 1, you may want to start at 0. Totally fine. You could have A sub 0, A sub 1, A sub 2, etc. You could start it that way. Doesn't matter. It's just a list. And there are 2 ways that we are going to generate this list. One is with a recurrence relation, where you find a subsequent term from a prior term. And there's a sequence that you have all heard of that is defined that way, where you find the next term, in the case that I'm thinking of, from the prior 2 terms. Anyone know what that sequence might be? Fibonacci. The Fibonacci sequence, where you start out with 2 terms, 1 and 1, you add them, you get 2, then you add those 2, the 2 and the 1 and get a 3, the 3 and the 2 and get a 5. So you use prior terms to get the subsequent term. So that's what we mean when we say recurrence. You need to know the prior term to get to the next term. And then the other way is with an explicit formula. And so with this method, the explicit formula method, that's the method we will use most. And you find your nth term by acting on the index value. So for example, to get A sub 3, we would put 3 into a formula and get a number. So perhaps it's n squared. So if it was n squared and we were at A sub 3, that term value would be 3 squared or 9. So that's the explicit formula approach versus the recurrence relation approach. Most of the time in math and science, we're doing that, the explicit formula. But there's all these kind of cool and oddball things that happen with recurrence relations, so we sort of dip in and out of that occasionally. But usually we're building a function from the index value that's going to generate the term value. So for example, let's talk about notation first, then we'll do some examples. So for a sequence, we always use the braces, the curly brackets, to indicate sequence. This is a really common way to indicate it right there. This is another way. This is the most common way, though. We just do that. When we are in calculus and above, we just assume it's infinite unless they tell us otherwise. We assume if we see a sequence that n is going to go from 1 to infinity, that it is a counting number, 1 through infinity. When we have a series, we are going to assume the same thing. A series means you're adding terms together, and we will assume in calculus and above that it's an infinite series, that we're adding an infinite collection of numbers together, unless otherwise stated. Like they'll tell us, add this finite sum, or consider this finite sequence, which means a finite set of terms. But in here and beyond, you usually just assume n is a counting number, 1 and up. So consider that it's infinite. Now, when we think of this explicit formula method to create the terms in a sequence, so there's our function right there. Right? It's a function. The big difference between these functions and other functions that we have looked at in this class is that these sequence functions are discrete, not a continuous curve. Because we are putting in integers, positive integers. You stick in 1, you stick in 2, you stick in 3. You're not putting in 1.1 or 1.2 or pi, right? We're only putting in positive integer values. So when we look at the graph of one of these sequence functions, we just get a collection of dots. Right? So it's a discrete function. Right? So not continuous. No dots are connected to each other. So that's the big thing. So the domain, but it is a function. It's a function. And anytime we have a function, we can talk about domain. And again, usually we think of the domain as the set of non-negative integers, the set of counting numbers, sometimes the whole numbers where you start at 0. But you could also start a sequence at 5 if you wanted to. You could start it at any number that you want, any integer.
Can it be negative, like -7?
Technically you could, but we usually don't. It's kind of like time. Usually we start at time as 0. But you could. You could have an index value that's negative, but we won't do that, but you could do that. The most famous sequence of them all is the harmonic sequence. The harmonic sequence is the sequence 1 over n as n runs 1, 2, 3, etc. That is the most important sequence that you kind of see. As we're going through this chapter, I'll put the Desmos stuff here so you can kind of see. Desmos is really nice for sequences and series. You can build things pretty easily. And I'll put the code over here just so you can see it if you want to try to do it. It's pretty easy. So I have a slider here, and you can slide it. You can set up a slider easily in Desmos. And here I set n to be 16, so there's going to be 16 dots. Here's how you plot a dot or a point in Desmos, n comma a of n. A is the function up here. So when we put in 1, we get 1. The y value is 1. When you plug in 2, you get 1/2. When you plug in 3, you get 1/3. When you plug in 4, you get 1/4. And so it's just a subset of the curve 1 over x. So 1 over x would be a continuous curve. Right? It's an infinite collection of points in that continuous curve. The sequence 1 over n is a subset of that. It's also an infinite collection of points, but it's a smaller infinity. If you've ever looked at cardinal numbers, there are different levels of infinity. Like the integers is sort of the smallest infinity, but then when you get to the irrational numbers, that's a bigger infinity. The set of reals is a bigger infinity. So even though the set of dots is infinite, it's a subset of an infinite set also. But we can think of the sequence as a subset of a continuous function. All right, so usually in math, if you see an x, it means continuous, and if you see an n, it means discrete. So n is usually an integer, positive integer usually, could be 0, usually not negative. So that's the difference between a continuous function and a sequence. And we're going to see some theorems that will say, hey, if you've got your sequence, consider the continuous function from which it is a subset. And you can do some calculus. Like, we all know now that if we're doing calculus, i.e. integration, differentiation, your function has to at least be continuous, right? You can't take the derivative of a sequence. There's no tangent line on a sequence, right? For a tangent line, there's got to be a continuous function that tangent line is attached to. So we can't technically do derivatives and integrals of sequences, but what we can do is say, oh, well, let's look at the continuous function that it's a subset of. We can do calculus on that, and that might give us some information about the sequence. Okay, so first and foremost, just like in Calc 1, when you first started dealing with functions that had asymptotes and things, you took limits. Same idea here. We want to take limits. We want to be able to take limits of sequences. And this really is no different than what you did in Calc 1, taking limits. And so it means exactly what you sort of expect it to mean. We say that the limit of a sequence is going to exist, and that the sequence converges to L if that limit does in fact exist. And that means that the terms are getting arbitrarily close to a single number. That's what it means for a limit to exist. It means that the terms have to get, sometimes we say infinitesimally close or arbitrarily close. You know, we can get as close as we can imagine. And if the sequence doesn't converge, it diverges. The sequence does one or the other. It either converges or it diverges. If it converges, it gets arbitrarily close to a single number. If it doesn't get arbitrarily close to a single number, the sequence diverges. And then Calc 1, you might have done the epsilon thing. You know, and the idea in your mind is that if the limit is going to exist, no matter how small you pick an epsilon, eventually the rest, in Calc 1 you would have looked at the tail of the continuous function. Here we look at the tail of the sequence. The tail is going to be within epsilon of that L value. So you sort of think of this little interval, this epsilon interval, and if the limit exists, it doesn't matter how small you ratchet that interval, the tail will be trapped inside that little tunnel. But we're not going to get that detailed in terms of looking at epsilon. So in Calc 1, you first looked at the basic limit, 1 over x as x goes to infinity. Here we're doing the analog. We're just looking at 1 over n as n goes to infinity. Clearly, that limit is 0. Right? If the denominator is getting bigger and bigger and bigger, the fractions are getting smaller and smaller and smaller. So that's one of our basic limits. The limit of that is 0. So that is the harmonic sequence. We have another sequence that's very closely related to the harmonic sequence, called the alternating harmonic sequence. The alternating harmonic is what it sounds like. We take the harmonic and we just swap the signs. Plus, minus, plus, minus, plus, minus. So there's a picture of the alternating harmonic. You can see from the graph that the limit of it is also 0. And in our mind, we're doing the same thing. We're thinking, okay, the numerator is flopping around between -1 and +1, right? Just back and forth. But the denominator is blowing up. The denominator is going to infinity, which means the term values are still approaching 0. They're not approaching 0 in the same way that they were in the last example. They're oscillating, but getting tighter and tighter to y equals 0. Okay, so that limit still is 0, though. Those terms, each term is progressively closer to 0. So the limit is 0. This numerator here, for an alternating sequence, we call that the switch. So this is just switching back and forth between positive and negative. So we call that the switch. And it doesn't matter whether if it's -1 to the n or -1 to the n plus 1, it's still called a switch. If you have something in there that's just changing, you can even set up trig functions like sines and cosines to have values that are either +1 or -1. So we'll call it a switch. And when we say alternating, we mean alternating. Every term is alternating. Not plus, 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 minus, minus, plus, plus, plus. Right? If we say an alternating sequence, we literally mean alternating. Every term is changing sign. You can have sequences where there are groups of positives and groups of negatives, but that's a little different. It wouldn't be called alternating. So let's take a look at some sequences here. So this says find the next two terms of the given sequence and then find a recurrence relation and then find an explicit formula. So sometimes one is easier to create than the other. Sometimes it's easier to write it as a recurrence relation. Sometimes it's easier to write it as an explicit function. Just kind of depends. Now the first part of this is pretty simple. So the first part says, what are the next two terms? And we kind of clearly see that we are just adding 3 repeatedly. So we're adding 3 repeatedly. So our next two terms are going to be 14 and 17, and then it keeps on going. So pretty straightforward in this case. Sometimes finding usually finding the next number is pretty easy, but sometimes finding the recurrence relation or the explicit formula can be just a little more subtle. Okay, let's see. So now it says find the recurrence relation. So we want to figure out how to get to n plus 1, the n plus first term, so a sub n plus 1. How do we get to it from the prior term?
A sub n plus 3.
A sub n plus 3, yeah. So this is going to be the recurrence relation, pretty straightforward.
And do you also need to define where the first term starts?
Technically, we would have to say for a recurrence relation, you need to know where we're starting. Right? We need to know what's the first term. We can't add 3 to a term unless we know what term we're adding 3 to. So what we normally will do is define the very first term. So we'll say that a sub 1 in this case is 2. So if a sub 1 is 2, then a sub 2 is going to be 2 plus 3, which is 5, etc. So we need to know the starting point.
And so you could do a sub 0 equals 2?
You could do a sub 0 is equal to 2.
Okay.
Absolutely. If you did a sub 0, so here we're going to let the n's, so if we know that n is, if we already have it, if we call that one a sub 1, then we're letting n go from 1 to infinity. If we call that a sub 0, we'd let n go from 0 to infinity. Yeah. Did they? Yeah, they did. They wanted us to do 1 to infinity, so. Okay, so now find an explicit formula. So to find an explicit formula, what we want to do is think about the index values. So I'll usually put the index value right below them and see if I can figure out a pattern. So we want to try to figure out how to get to the term value from that index. And what's helpful, like if you're good with spreadsheets, that's a good way to try to find patterns. You can have a column that represents n, a column that represents whatever, 2 to the n, 3 to the n, 3n plus 1. You can just do columns and sort of see if you can find patterns. Because it's not always obvious. It's definitely not always obvious. So let's first just do this kind of thing. So if we start with n values in this left column, we can just do things. We can, do some common things like, oh, well, let's see if we multiply everything by 2, do we see a pattern? If we multiply everything by 3, do we see a pattern? So that's kind of the idea. It's really, a process of trying to, find stuff. And does anyone see a pattern yet?
3n minus 1.
3n minus 1. If you look at the 3n column, you're like, oh, 3, 6, 9, 12, those are all one more than the terms that we're trying to build. And the other common types of things are, maybe a 2 to the n or a 3 to the n. So we just sort of look at some basic kind of arithmetic on the n value to see if we can discern a pattern. I would not ask you to do something like this on a test unless it was pretty straightforward. You can come up with patterns that are very difficult to discern. But we would be, if this was on a test, we would definitely pick something that was, reasonable. So here we're going to say that a sub n is 3n minus 1. And, so the first term, so we're going to say n would go from 1 to infinity. So a sub 1, plug in the 1, you get 3 minus 1, which is 2. A sub 2, 6 minus 1 is 5, etc. Now sometimes, let me just show you a piece of notation. You're probably not going to see it too often, but sometimes writing this is just a little bit of a headache to write n is equal to all, that. So a lot of times in math we represent sets, and we use this epsilon to represent element. So it's the Greek letter E, epsilon, represents element of a set. And does anyone know what the symbol is for the integers?
Is it that double-sided R?
So the double-sided R is for the real numbers. The double-sided Q is for the rational numbers. So this is the set of reals. This is the set of rationals. They use Q for quotient. For the integers, they use a Z. I don't know why Z, integers, I don't know, not sure.
Sure.
And if you wanted to, you can put a superscript up here. So if you said R plus, that would mean the positive real numbers. If you said Q negative, that would be the negative rational numbers. Z plus will be the positive integers. So you'll see this notation as you start looking stuff up on YouTube and things. So you could abbreviate this and say n is an element of the positive integers. Be just a quick way to indicate that. So you'll see that a lot where they, instead of writing out this all the time, n's a positive integer. But either way, does not matter. Okay, so let's look at the next one. Same idea. First, we're going to look at the next two terms in this sequence. So we have pretty obvious. What are the next two terms going to be? So we're doing repeated division by 2 or repeated multiplication by 1/2. So if we did want to even go further than just the next two, that would be our pattern. And I just put a couple extra terms in there to make it clear that we're never going to be negative. Right? These terms will never go negative. They're always going to be positive. And the recurrence relation, to get to a subsequent term, we do what to the prior term? Divide it by 2, multiply it by 1/2, and we have to indicate that our first term is what it is 64. So that tells us where to start. Now let's do the harder part. So the harder part in this case is going to be finding the functional description of this sequence. So again, building a table is usually super helpful. Going down to 5 hopefully is enough. And one thing that we all probably are noticing right away is that each one of these numbers is a power of 2. Each one is a power of 2. So it will be helpful if they're all powers of 2. Let's look at this column, 2 to the n. So 2 to the 1 is 2, 2 to the 2 is 4, 8, 16, 2 to the, that's 32. Okay. All right, so that's not quite it exactly. Any ideas?
To the negative n.
64 over
To the negative n.
Wait, I heard it 64 divided by 2 to the n?
Yeah.
Let's just check first and see if that will work. Okay, so 64 divided by 2,
32.
32, so definitely not 64. If we were
128.
If we were going to go this route, we would start with 128. So let's see if that works for all of them. And a lot of times there's slightly different ways to get at this. So, okay, we plug in the 2, so plug in the 1, and we get 64. So that one checks. So our first term is 64. If we divide that by 4, that's going to be 32. Divide that by 8. So we're really just dividing by 2 again, right?
Because that's effectively if you
Effectively, we're just putting an extra factor of 2 in the bottom.
up there.
Okay, so did that work?
128 is 2 to the 6.
Yeah, that looks good.
If you just write that as
Yep.
2 to the 6 over 2 again. That's
So that is definitely one way that we could
6 minus
write this. So we could say a sub n is going to be 128 over 2 to the n.
And does A start at 1?
A starts at, n starts at 1.
Yeah, n starts at 1.
N starts at 1.
So you could do like, because n to the 6 is 64, right?
2 to the 5. 2 to the 4 is 16. 2 to the 5 is 32. 2 to the 6 is 64.
So you can do
2 to the 7. So here's another way we could do
n
it.
to the negative n of
So
plus 7.
do you agree that 128 is 2 to the 7?
Yeah.
2 to the 7. So we could write this as 2 to the 7 minus n. That's another way we could write it. Any of those would be totally legit. So we could write it like that. Could write it like that if we simplified it.
Honestly, a good starting place is just 64 over 2 to the n minus 1. Make the bottom
Yep,
0,
that.
or make the bottom 1 and then the top.
And the top is what we want it to be.
Yeah.
Yep. So if we want the top to be 64, make a 0 exponent in the denominator. Absolutely. So some other columns that you might think about, we could be doing 2 to the negative n and just sort of see, there's all sorts of ways to get to a pattern that's going to work. 2 to the negative n is a reasonable thing to do because that's going to create things, that's going to help things shrink. Multiplying by 1/2. So, all right, let's try this one. So here, next two terms are what?
36, 49.
36 and 49, so clearly we're dealing with squares. All right, so now to do a recurrence, we want the next term to be based on the prior term. So this one, the recurrence part's going to be harder than let's just write down the function form. Isn't the function form simple?
N squared.
Right, that's just n squared. So that form is going to be easier in this case. All right, any ideas for the recurrence?
Well,
I'm going to put the indices down here. So let's just pick one as a starting point. Let's suppose we start here. Okay, we're at 9, and we want to get to 16. Can you
7.
say that again?
Difference of 7.
So the differences are not going to help us because the differences between these squares are weird, right?
Yeah.
3 and then 5 and then 7 and then 9.
That's a linear sequence, isn't it? 3, 5.
Not linear.
Well, not linear. Sorry. It's just all the odd numbers.
So how can we get at that?
2n plus 1.
Not quite.
Oh, I guess we don't have, since we don't have the indices, you can't find.
So if everything is based on the indices, right? This is sort of 25 because of its index. Is there a way, can you see a way to go like from this down to its index?
Square root.
Yes.
It's adding odd numbers though. 3, 5.
I just heard the key. If we take the square root of the prior, so we're trying to get to the 16, if we take the square root of the prior, that drops us down to here, and then we add 1, and then we square it. Exactly. That'll do it.
That'll work.
That'll work. That'll work. That will work. So there is the recursive way to get at it, and there is the functional way to get at it. And again, one is usually easier than the other. But
But you could use that recursive method if you had a non-1 starting point for the sequence that's defined by that. So if a to the n was like 20 for some reason, and you're still using n squared for your.
what was your point? If you could do the
like,
recursive
you could still use the recursive to get from one unit to the next. If
Yes.
You
if you had
you
a
wanted the same ratios, but you had a different.
different starting value.
You could theoretically still use it.
Yeah, you could do, and you could still use the function one that way too.
Exactly.
Yeah, absolutely. Absolutely. Okay, so let's take a look at some specific sequences. So write out the first few terms. If the sequence appears to converge, make a conjecture about it. If it appears to diverge, explain why. Okay, so one thing that I noticed was a weak point on the exam was finding some limits when we were doing improper integration. And what I noticed, which is what I also mentioned in class, and some of you just ignored it, if you have a negative exponent, it's usually harder to see what is happening. And my recommendation was just put it in a form with a positive exponent because it's usually more intuitive. And so there's a few folks that just looked at this and wrote infinity, something similar to this, and wrote infinity. Whereas if you wrote this without a negative exponent, I would hope that it would be really obvious that, oh, the denominator is going to infinity, so the fraction is going to 0. This was especially problematic when we had, I'm picking n instead of x, I don't know why. Like if we were going to a constant like 2, and down here we had n minus 2, and we were going from, say, the positive side here. And let's suppose that this was written as n minus 2 squared to the negative 2, something like that. It's really tempting to say, oh, that's 0. 2 minus 2 is 0, we're done. No way, right? If you write this with a positive exponent, you have n minus 2 to the positive 2 down there, and n is going to 2 from the right. What is this limit going to be?
Positive infinity?
Positive infinity. This denominator is going to 0. If the numerator is constant and the denominator is shrinking to 0, those fractions are exploding, right? You think in your mind, 0.1, 0.01, 0.001. If you start dividing by numbers that are getting closer to 0 and the numerator is a constant, you're creating things that are getting larger. All right, so it's very easy to make mistakes with your limits when you have negative exponents in there. If it is not crystal clear what that limit is, like if you're not super comfortable with negative exponents, get rid of them. Get rid of them and then look, is the denominator going to 0? If the denominator is going to 0, then the fractions are going to infinity. If the numerator is going to 0, then yeah, the sequence is going to 0. But it's always easier. 99.9% of the time, it is easier if you have no negative exponents, because you can just sort of visualize it much simpler. Because then you're saying the bottom's going to 0 or the top's going to 0. I know what happens in those two cases. So when we look at this thing here, as n is going to infinity, I hope it's totally obvious that this limit must be infinite. 10 to the n is growing without bound as that n value is climbing through the integers. Okay, so here we would say the limit of 10 to the n minus 1, that is going to be infinity as n goes to infinity. And so this is one of those other basic limits. So we know that 1 over n goes to 0, and we know that if we had something like just the limit of n as n goes to infinity, that obviously must be infinity. So it's that same kind of idea. 10 to the n, the base is bigger than 1. And if you have a number that's bigger than 1 for the base, That's going to drag to infinity. 2 to the n, 3 to the n, 4 to the n, 5 to the n. But if the base is less than 1, where does that go?
0.
So 2 to the n is going to go to infinity, but 1/2 to the n is going to go to 0, right? Because a fraction multiplied by a true fraction multiplied by itself, a proper fraction, will get smaller as you multiply it by itself. And an integer, a positive integer multiplied by itself is going to drag up, fraction is going to drag down. Okay, so that limit is a basic limit. It's done by inspection. That's infinity. Now let's take a look at this one. So in 40, we have the limit of 1 minus 10 to the negative n as n goes to infinity. Again, get rid of the negatives. If you get rid of the negatives, it's just easier. So we know that to get rid of the negative, we just move the base down below, change the exponent to positive. So now we're in that situation that's kind of reverse of this stuff. Here the denominator is going to infinity, so the fractions are going to 0. So this fraction right here, as the denominator is increasing, the fraction's going to 0, so our overall limit is 1. Here's a picture of this sequence. Horizontal asymptote at 1. Right, that's what horizontal asymptotes are. In pre-calculus and college algebra, you called it a limit at infinity. Well, actually, you didn't use the word limit. In Calc 1, you call it a limit at infinity. In pre-calc, you call it a horizontal asymptote. You call it end behavior, what's happening out in the end of the function. All right, so, and of course, when we look at this picture, that doesn't prove that the limit's 1, but it sure is convincing. We would want to do the math to confirm it, but you know, that's a strong indicator that the limit is 1. Okay, so let's take a look at a couple of recurrence examples. So here's a recurrence relation. So recurrence relation is going to build the sequence, the starting value of 1. So here I've got the values over here. We're starting at 1, and then we do what it says to do. We divide it into 10. Second value is 10. Divide it into 10 again. Well, that's back to 1. Divide it into 10 again. That's back to 10. So we can see by looking at a little sequence in Desmos that this sequence is going to diverge. Right? It's not going to. It cannot approach a single number. And a sequence, a function, cannot have 2 limits. It's got 1 limit if there is a limit. This thing clearly does not have a limit. Okay, so what we would say here is that the limit of 10 of a sub n does not exist. And that's all we can say. Like sometimes in algebra, Calc 1, you can say the limit is plus infinity, then the limit is minus infinity. Those limits also don't exist. Right? So if you have something like the limit of say, n squared as n goes to infinity, this is true. It does not exist. That's true. For a limit to exist, there is a number. Infinity is not a number. There is a number that the terms are getting arbitrarily close to. So this is correct. But it is not the most correct. You can say more. You can say that this limit does not exist in the sense that the terms are getting large without bound. So this is better. This is true. It's true that the limit does not exist, but this is better because it's more descriptive. You can't always get more descriptive. Like if you have something like the limit let me say as x goes to 0 of 1 over x. So that limit there, we cannot get more descriptive than this. right? Because if you look at the graph here, the graph of 1 over x looks like that. As you come in from the right, it is positive infinity. As you come in from the left, it's negative infinity. But you can't say that the two-sided limit is either plus or minus infinity because it's, it's different from the different sides. So we can't be more descriptive there. Whereas if we had something like the limit as x goes to 0 of 1 over x squared, now that's totally different. Here we could say that the limit is 1 over x squared is going to look like this. And so we can say that this two-sided limit is infinity. We can say that, and this is actually a little bit misleading. We often will say the limit is infinity. That's not what we really mean. We mean the limit, this notation, this equal sign here is not a real equal sign. It means that the limit doesn't exist because the terms are getting close to, or moving towards infinity. And we say it all the time, oh, the limit is infinity. Technically, we should not say that.
The limit goes to.
The limit goes to infinity. The limit does not exist because the terms are going to infinity. So we've got to just be a little careful because it makes us think that the limit exists when it doesn't. We're not using the equal sign there to mean it is equal to. Right? So it's a little misleading. Okay. Now here's another recursive one. So this one clearly does not exist, right? It's jumping around. You could say, one descriptive word you could say by oscillation. That is one other descriptive word that sometimes is used because it's bouncing back and forth. So here's another recursive sequence. The terms here, we look at the terms. First term is 2, second term is, all the terms are 2. So that sequence appears to converge, right? A constant sequence converges to itself. It's getting arbitrarily close to itself. Now, to prove that this recursive sequence converges, we can use this clever trick. If you are reasonably assured that your sequence converges, you can use this trick. So we're reasonably assured by looking at the first, 6 terms, 7 terms of the sequence, we're reasonably assured that it converges. You can do this. You can assume, so if you're reasonably assured, assume limit of a sub n is equal to L. So we're going to say, okay, looks like the sequence converges. Let's just call the limit L. We'll say that's what it's going to converge to. And here is what we're going to do. We're going to take our recursive definition, and we are going to take the limit of both sides as, I need more space there, as n goes to infinity. I'll just squeeze it in. So we're going to take the limit of both sides of that sequence as n goes to infinity. Well, on the left, if you assume that that's true, isn't the limit of a sub n plus 1 also L? It just has the first term chopped off, right? A sub n starts at n equals 1, so there's a sub 1, a sub 2, a sub 3, a sub 4. If you look at this sequence all by itself, a sub n plus 1, and you're starting n at 1, just like we've been doing, then this sequence on the left, treat these as two separate sequences all of a sudden. This one starts at 1, this one starts at 2, but the tails are the same. If you have a limit of a sequence, if you have a sequence that converges, you can chop off the first term, or the first 10 terms, or the first 100 terms, or the first 1,000,000 terms, and it still converges to the same thing. Everyone agree with that? Convergence at infinity is all about the tail. If you chop off the leading terms, no big deal. That's not going to change the limit. So this is going to create an algebraic equation. The limit of the sequence on the left is L, because we said the limit of the sequence is L. And the limit of the sequence on the right is L. So we end up with a little algebraic equation that you can solve for L. Let's solve that for L. Let's subtract L over 2 from both sides. Equals 1. Multiply by 2. There's your sequence limit value. So if you look at a sequence that's given to you recursively, and it looks like you're pretty sure it converges, you can find what it converges to by doing this little process.
Kind of reminds me of almost like a score. You have to have, you're proving it beyond reasonable doubt.
Yeah. So this is a little different. Yeah, we assume if we assume that this sequence converges, then this is beyond a reasonable doubt. If.
Mathematical.
But there's a little ambiguity there because we're sort of just looking at a description of the sequence and assuming it
You
converges.
could theoretically have a sequence that has a plateau that lasts 200 terms and then drops off
Yeah.
or something.
Yeah.
Where you can look at the numbers and you're like, oh, it's always 2, and
Yeah.
then it hits a point where it just drops.
And there is a really freaking cool example of exactly that. And I can't remember what it is off the top of my head.
One, I think it's the sums of like fractions
Yeah.
that is like a plateau that sits at pi for
Forever.
like 15 terms.
Yeah.
And then
And
it
then all of a
drops off
sudden
by
it
a
dips.
tiny amount. I
Yeah.
can find a video.
Yeah, that's the one I'm thinking of. It's
Yeah.
like you're really sure that it's doing one thing, and then you go out like 15 terms, and all of a sudden it changes. It's like, wait, what? How'd that happen?
Just like, yeah.
Or the prime number that, like, we keep adding digits, prime, and then it stops being prime.
Like
If you can figure out anything to do with prime numbers, you'll be rich.
Or like just a piecewise function that's defined as
Piecewise, you can
Like,
make things. Piecewise, you can make any behavior you want to happen.
if it's just stuck at a value for a while and then
Yeah,
it
you
drops
can.
to a certain one, it is like if you just had the graph and you're like, it's clearly 1 the entire time. It goes to 1 at infinity. And it doesn't.
Yeah, but with piecewise, you really have a lot of. You can make anything happen with
Piecewise.
piecewise. So that other example, though, I'll look it up too, is not a piecewise thing. It's like
not.
it's a thing
I
that you.
think it's the sums of the signs of odd fractions. I think it is an infinite series. It's like the sums of odd fractions, and then if you keep adding terms, eventually you reach a point where
I
it's
just cannot remember. I can't remember. Yeah, find one you're looking at, and I'm going to look up the one I'm thinking of. Okay, so now, so this first section, 10.1, is an overview. We just did an overview of sequences. Now we're going to do a little overview of series. So when you think sequence, you think commas. When you hear series, or you try to visualize or think of a series, the big difference is that instead of commas, you have pluses. So a series is when you add the terms of a sequence. So we've got our basic sequence up here, our ordered list of numbers, and then we want to add them all together. So that takes the sequence of terms and turns it into a series. So we turn our sequence into a series by adding the terms. Simple enough, right? Sounds pretty simple. We just add the terms instead of list the terms. What we are going to do to analyze our series, we are going to build another sequence. So we've got our sequence of terms, we now have our series, and now we're going to build a second sequence. And that second sequence is going to be the key to figure out whether the series converges or diverges. This second sequence is called the sequence of partial sums. And they are what you think. They are the sequence of partial sums. So we start with S sub 1 being just the first term, and then S sub 2 is the sum of the first two terms. So we're kind of doing this thing where we look at that, and then we look at that, and then we look at that. So we're kind of just adding one extra term at a time. So we're slowly inflating the sum. Add one term, add one term, add one term. And this is the sequence that will tell us whether the series converges or diverges. So that is what the sequence of partial sums looks like. Okay. So S sub n, if we want to look at the nth partial sum. The nth partial sum is the sum of the first n terms. Okay, that's what S sub n is going to mean, sum of the first n terms. Add up all the way through A sub n. And here is the shorthand notation using capital sigma, sigma, S for sum. So this is a partial sum. That is a finite sum, right? You're adding up n, a discrete number of terms. It's not an infinite sum. This would be an infinity up at the top if it was an infinite sum. So here, they're being very explicit in telling us, okay, it's not an infinite sum, it's just a partial sum. We're going to stop at the n value that is whatever it is up here. So it's going to be just a partial sum. Okay. Now in your mind, this is what I'm hoping you're sort of seeing. Like, let's suppose we have this, we've looked at this before. We can think of that number as being a sum of positive numbers. Whoops, want pluses. All right, and we already know, we've talked about this, that this is going to equal 1/3. And if you want to think of this in terms of partial sums, what you're thinking about is this sequence. You're thinking about the sequence. 0.3 is S sub 1. 0.33 is S sub 2. 0.333 is S sub 3. So here's S sub 1, S sub 2, S sub 3. And can't you see that this sequence is in fact getting closer and closer and closer to the 1/3, right? As we keep adding one more term, add a term, add a term, add a term, we're getting infinitesimally, arbitrarily close to 1/3. Right? Every time we put another 3 in here, we're getting a little closer to 1/3. And so that's the idea behind the sequence of partial sums, that for the series to converge, that sequence of partial sums must get arbitrarily close to some number. There must be a limit for that sequence. So if we take the limit, this is the sequence of partial sums right here. And if we take the limit of S sub n in this example right here on the right, we get 1/3. So in other words, this series, so this is the series, and we would say that this series converges to 1/3 because the limit of the sequence of partial sums is 1/3. So a lot of terminology is really all we're doing right now. So if we have this series, infinite series, we then look at the sequence of partial sums. The infinite series, here's the infinite series. If it converges, it's going to converge to the limit of this sequence of partial sums. So 1 to n, if you add up the first n terms, that's called S sub n. And if that sequence has a limit of L, then the series is equal to L. The series has a sum of L. The series converges to L. We say a whole bunch of things that mean the same thing. If the limit of S sub n, d n e, bless you, if it does not exist, we say the series diverges. So a series converges or diverges, just like a sequence converges or diverges. If the series doesn't converge, must diverge. One or the other. No ambiguity. One or the other. So we've got that fire drill at 11, so we're just going to push through to 11 and we'll have our break outside. Not miss infinite series stuff. So let's take a look at a specific example. So repeating decimals are really just infinite series. That's what a repeating decimal really is. So 1/9 is 0.1 repeating. We can think of 0.1 repeating like that. So you can think of this in a couple of ways. So there is the sequence of terms. Here is the infinite series. Here is the sequence of partial sums. So stare at that for a moment and make sure you sort of have the terminology. So we have the terms, and then we have the partial sums. So the terms is a sequence, the series is a sum, and then we have our auxiliary sequence that we build called the sequence of partial sums. And for us to analyze the series, we need to be able to take the limit of S sub n. Okay. Now, if we think of it visually, here's what a converging sequence of partial sums looks like. Remember that sequence of partial sums is growing if we're dealing with positive numbers, right? We're adding a term, adding a term, adding a term, so we're going up, right? We're adding terms. This sequence is growing, or right, the terms in the sequence are growing. So there's the first term is 0.1, second term is 0.11, third term 0.111. It looks pretty darn close to 1 1/9. All right, so this is at 1/9. 1 divided by 9 is that horizontal asymptote. They're not equal, obviously, right? You know that by now, that if you zoomed way in, that dot's not really on 1/9. It's just a smidge below, skosh below. So the limit of S sub n is 1/9. We are going to learn how to show that the limit of this is 1/9 very soon. This type of series is the most important type of series. It's called a geometric series. And a geometric series is where you have a constant multiplier to get from one term to the next. Can you tell me what we would multiply that term by to get to that term? We would, what is that? It is, we are going to do this. Let's talk about this part later. So it's going to be a geometric series. There's going to be a constant multiplier. If we factored out the 0.1, we would see this sequence we could see this multiplication by 1/10.
It's because we're looking at the sums.
Oh, we're looking at the sums. Thank you. Yeah, we're looking.
10.
Yeah, there's
That's
the
the one that's actually.
it's a geometric sequence right there. So we're multiplying by 1/10 all the way through. Yeah, thank
Partial
you.
sums is not geometric.
Yeah, the partial sums is not geometric. The sequence of original terms is geometric.
That's
And what we will see is that there is a way with geometric series that you can analyze them pretty easily. The long story short is that if you have a formula for S sub n, you just take its limit. So the question is, how do you find a formula for S sub n? And for geometric sequences, it's very easy. We'll get to that. And so this is going to be called a geometric series if there is the constant multiplier. So here we see the constant multiplier of 0.1, right? We're multiplying repeatedly by 0.1. So that will be a geometric sequence. This will be a geometric series if there's a constant multiplier. And when you have a geometric series, you will be able to find S sub n. So if S sub n is known, take its limit. So the big question is going to be, all right, we've got this series. Geometric are going to be really nice because we can find S sub n and then take the limit. Taking limits is easy. Many series, you cannot find S sub n. And that's why we have this horrible stuff right here. All these convergence tests. This triage nightmare is because most series you cannot find a formula for S sub n. Like if you just think about adding up an infinite collection of numbers, unless there is a really strong pattern, you are not going to be able to find a formula for S of n. And that's what this whole business is all about. We are going to really like geometric series because we can find S of n and take its limit. But when you can't find S of n, then that's what all this stuff is for. That's why infinite series are so hard. Because most of the time, we cannot find a formula for S of n. We will look at the ones that you can find a formula for first, because those are the easiest ones, right? We'll stick with those first. Dustin?
On like impossibly hard stuff now, do they just use computers to find them?
So this is where we are going to use. So when we're taught the real world problem to solve is the differential equation. So differential equations we can generate easily. You go out, you collect your data, you can build a differential equation very easily. Like that's not a big deal. So the issue is that the solution to a differential equation, the chances of it being an elementary function, e to the x, sine of x, cosine, zero. And so that's where we say, okay, well, the solution must be an infinite series. We're going to see that infinite series are really functions. And so that's where the infinite series is going to come in. And then we can use a computer to go out far enough in the series to get accuracy to do whatever we need to do. You know, if we're shooting a missile or if we're trying to blow something up, we can figure out exactly what the threshold is. We go far enough out, you know, that we can get accuracy to what we need.
They really are teaching us world domination.
World domination is important.
And you only do
If
it
you're not the
for
dominator, you are
missiles,
dominated.
Explosives.
Right, all that stuff. All right, so
Starts in Calc 2.
it all starts in Calc 2. Yeah. Yeah. World domination. So I used to live on a military base out in the Marshall Islands. So back when I was in high school, my dad was an engineer working on, in the Marshall Islands, that's like the US government's primary tracking station for satellites, missiles, and submarines. And so anything that's launched from China or Russia, the Marshall Islands is positioned perfectly on the horizon that you get a sort of heads up right away. And so it's really interesting living out there. One of the weird things was that the Russian sub that was watching us, you could see it during low tide right off the island, you know, the little periscope looking at the island, totally weird. And we would shoot, the US government, this was back in the 80s, so we were working on the Star Wars program. So the US government was shooting missiles from Vandenberg, California out to the Marshall Islands, and the big idea was to try to intercept them. And so we go down to the beach as high schoolers with a cooler of beer, you know, because they always did it at night. And you could sit on the beach and watch, you know, the missiles would come in and land in the lagoon. And then when they were trying to intercept them, you know, that was very hard. Usually they missed at first. And then the next day, I was my swim coach literally had a yellow submarine that was like 15 feet long, and he would be out there in the lagoon, and the second that thing hit the lagoon, he'd hop in his little yellow submarine and go retrieve it because they didn't want the Russians to retrieve it, and bring it back to the island. It was totally bizarre. It felt like a cartoon, like sitting on the beach drinking beer, the missiles are coming in, the yellow submarine's taking off. Like, really? Is this a Beatles movie?
That was his job, right? He
That's
wasn't
Jim
just.
Sheldon.
That was his job.
Okay.
That was
No,
his
he's
job.
just a random swim friend.
Yeah,
Like,
yeah.
oh,
Built
this
his
is
own.
If he built his own yellow submarine.
Yeah.
And that yellow submarine is now in a museum in Hawaii that I went and saw recently. I was like, oh my gosh, that was the submarine
That's
that
cool.
Denny used to ride out and pick up the missile in.
Classic.
Okay, so infinite series. Here's another one. So it says, find the first 4 terms of the sequence of partial sums. So S sub n, this is the sequence of partial sums. So it is going to look like this. This is what the sequence of partial sums looks like. Sequence of partial sums. Then make a conjecture about the value of the infinite series. So let's go back to algebra for a minute. So we kind of know from, you know, algebra classes that the limit of this sequence of partial sums is 2/3, right? We know that the limit of S sub n is going to be 2/3. Maybe you don't know how to show that, but we definitely intuitively know that that's true. All right? And maybe it's more obvious, maybe this is more like what you want to conclude. Maybe you can see that that's for sure. We just keep having these repeated sixes. But that is equal to 2/3. And so this algebra problem here, to make sure that we all know, does everyone agree that 0.6 bar is the same exact thing as 2/3? How do you take a repeating decimal? So if we let x equal 0.6 repeating, and we want to turn it into its rational form, every rational number has a decimal form and a fractional form. If we want to change this, we do the whole multiply by 10 business. And then your decimal turns into an addition. So you get 10x is equal to 6 plus 0.6 repeating. But we already said 0.6 repeating is x. So now we have 10x is equal to 6 plus x. So we get that 9x is equal to 6, divide by 9, and we get the 2/3. So that's how, in algebra, we would show that this infinite series converges to 2/3. And again, if an infinite series converges to a number, we literally just say that infinite series is equal to that number. So infinite series converges, it is equal to whatever the number is that the sequence of partial sums converges to. Those two things are the same. Which again, I mentioned this one time before, decimal representations of numbers are, no, I don't want to say that right now. I don't want to say that. Okay, so that and that are the same. Infinite series, 2/3, these are the same. What do you think this infinite series converges to?
5.
This is going to converge to 5. All right, so if we want to prove that that converges to 5, we're going to look at this part. That's the tail. The tail is going to converge to, let's see. So same thing, we're going to say x is 0.9 repeating. Multiply both sides by 10. Bust apart the decimal point into an addition. Once again, we get 9 plus x. There's 10x. So we are going to subtract the x, get 9x equals 9. So x is equal to 1. So that tells us then, if we wrote this in two pieces here, we would say that this is going to be 4 plus 1, which is 5. So that is what that infinite series converges to. And here is where I was going to say a minute ago, which I will say here, is that 0.9 repeating is the same thing as 1. Same thing as 1.
Is that because we're evaluating the limit ultimately of that?
These are equal.
Huh.
So these are not equal just because of the limit. They are equal. If you imagine numbers on the number line that are distinct, so not equal, there is a measurable difference between the two, right? And so by contradiction, you can show that these two are equal. Because if you assume they're not equal, there's a measurable difference between them. And any measurable difference that you claim is the difference between them, I can show you that's false, that they're actually closer than that. So, and that's sort of that whole limit idea, right? If there is no measurable difference, then they must be the same. Okay, so we can, so that this kind of shows us that the decimal representation of numbers, both of those can be considered as decimal representations of a number. Decimal representations are not unique. 0.9 repeating and 1.0 represent the same exact number. So decimal representations are not unique for the numbers. All right, let's see. We're gonna make it through this slide. Is it really gonna happen right at 11?
Probably.
Probably. Everything else, hey Troy, everything else feels a little off this semester though, so maybe it won't happen right at 11.
Hey, there was no Zamboni today, though.
It's a red herring.
There was. You're like,
was?
yeah, you're like the dog. What's
There
that
was a
dog?
Pavlov train.
Yeah.
I did not.
He doesn't even hear it anymore.
Yeah. I knew it.
I did.
Yeah,
Not here.
I was trying to actively not hear it, but I couldn't succeed.
If we
Loud.
don't acknowledge it exists, it doesn't exist.
Right? We didn't mention it. Bryce never heard it. Okay, so this says find the first 4 partial sums. Okay, so I've got them down here. We're looking at this series, 1/2 to the k, 1/2 to the k, however you want to describe it. These are the terms, so we have repeated division by 2. The sequence of partial sums is found by looking at the first term, then the sum of the first 2 terms, then the sum of the first 3, and then the sum of the first 4. And so the question that I posed a moment ago was, how do we find a formula for S sub n? Because if we can find the formula for S sub n, all we do is take the limit of it. That would be easy. So let's see. This is an example of a geometric series. Because this sequence of terms, how do you get from one to the next? Multiply by 1/2, right? So there is a common multiplier of 1/2. To get from term to term, you multiply by 1/2 repeatedly. So that is a geometric series. So let's see. Now we're looking at our sequence of partial sums here. So here is what our sequence of partial sums looks like. Our sequence of partial sums. We've got 1/2. So here's where we can't always find a pattern easily. If we can, we're golden. So there's our sequence of partial sums. So the question is, can we find a formula for S sub n? If we treat, and geometric series are going to be the easiest possible ones. Do you see the pattern for the denominator? What is it? N to the?
2 to the n.
So we're going to take this and raise, so this is going to be 2 to the 3, this is going to be 2 to the 4, this is going to be 2 to the 2, this is 2 to the 1. So
This is the denominator of the last term, which is defined as 2 to the k.
So it's 2 to the n. Everyone agree? Denominator, 2 to the n?
Yes.
And now if we look at the numerator, the thing about geometric series is that the numerator is always going to be related to the denominator. And I chose one that's pretty obvious. The numerator is
N minus 1.
2 to the n.
2 to the n minus 1. Yeah, we're just going to subtract off 1. Now, all geometric series you can find in S sub n, similar to how we're doing it here. There will be a formula that we will use a ton of, and you will get very familiar with. So then this is that. So if we split the fraction, now let's take the limit of S sub n. If we can find the limit of S sub n, that will be the sum of the series. And what is the limit of S sub n? The limit of S sub n is 1. Does everybody agree that the limit of S sub n is 1?
Yeah, because the other part goes to 0.
The other part goes to 0. So this fraction here is one of those basic limits. Numerator's constant, denominators go into infinity, so the fractions are squeezing to 0. So the limit of that is 1. So this infinite series converges to 1, is equal to 1, whatever you want to say. Lots of different ways to say it. So if you add up all those terms, you get 1. Now, this is interesting. So we've seen 2 specific sequences now, one that converged and one that diverged. We looked at the harmonic, and we said that the harmonic, I didn't prove it to you yet, but the harmonic diverges to infinity. But this one converges to 1. So the first thing I want you to make sure is crystal clear.
That converges infinity.
Oh, thank you. That converges to 1. First thing I want to make sure is crystal clear is that just because the terms are getting closer to 0, that doesn't mean the sum of the terms converges. Right? These terms are going to 0. The terms are going to 0. The limit of a sub n is 0. But that's not enough. That's not sufficient for the series to be finite, for the series to converge. So this series of terms also, this sequence of terms also converges to 0. But they are going to 0 faster than the terms above. So this is very similar to that improper integration thing. The terms have to be going to 0 fast enough in order to get convergence. So certainly the terms have to be going to 0 because you need to be adding negligible amounts out in the tail. You need to be adding things really, really close to 0. So they definitely have to go to 0, but that's not enough. They have to go to 0 fast. So we have two things we can say here. In order to get convergence, the terms must go to 0, but they also must go to 0 fast. So if the terms don't go to 0, what must be true?
Must diverge.
Must diverge. If the terms don't go to 0, must diverge. So if we're adding things that are getting, a little bit bigger, it must diverge. So for a series to converge, the terms have to go to 0 and they have to go to 0 fast. If the terms aren't going to 0, then we know we have divergence. For example, if we're adding the positive integers together, 1 plus 2 plus 3 plus 4 plus 5, those terms are not going to 0, so we know that series diverges. Does not converge to negative 112. Must diverge. Okay, so this series converges to 1. This series is equal to 1. So we've now done a brief overview of sequences, a brief overview of series. Now we're going to get a little deeper into both. So the deeper into sequences, what we want to do is basically find limits. When we have sequences, that's the main objective. What's the limit of the sequence? Does it exist? Okay, so back to sequences. Again, for us, upper level math, when we think of sequences, we think of them as functions. All right? Yes, there's the whole recursive thing. That's kind of cool, but 99% of the time, we want our sequences to be thought of as being generated by a function. So here is the continuous function. You can think of it like a parent function if you want, and the sequence function is a subset. So the sequence function is literally just the dots, but that parent function includes all the space in between. Okay? And so the first thing is that if we have a sequence that's defined as a function, and if we take that parent function, so the continuous function, if that parent function has a limit at infinity, i.e. horizontal asymptote, then the limit of the subset, the sequence, the dots, the discrete subset, is also L, including if the limit is plus or minus infinity. So what this tells us is that you can turn all the n's to x's and then do calculus. Like for example, if you have an indeterminate form, if you take a limit and you get infinity over infinity, what did we do if we had infinity over infinity? L'Hopital's rule, we took the derivative of top, derivative of bottom, reevaluated the limit. So we can now do that. Now technically, we shouldn't be taking derivatives of expressions that are discrete, but that's what we're going to do. If we wanted to be really formal, we could say, consider it as x over x plus 1, and then when we take the derivative, we take the derivative, then when we take the limit, we take the derivatives of the x's. But it doesn't matter. In this class and beyond, we always just take derivatives of the n's anyway. Okay, so here is a converse that's super important. Let's see, so let's make sure we have 10.1 down. So if in 10.1, it says, if the limit of the parent function is L, then the limit of the sequence is also L. So if the limit of continuous is L, limit of discrete is L. The converse is false. The converse is false. In here, so we have these dots right here. So there is an embedded sequence. And the limit of that sequence is what? 1, right? Each of the values is 1. That's 1 right there. So the limit of that sequence is 1. That does not mean the limit of continuous is 1. The limit of the parent is not 1. Can you see that? Right? What is the limit of this wiggly sine curve?
Does not exist.
Does not exist. It's oscillating. That limit does not exist. That parent curve does not approach a single number. So the parent curve does not have a limit. Its limit does not exist. But this embedded sequence here does have a limit. Right? Those black dots are converging to 1 because they're each equal to 1. So just because there is an embedded sequence that converges doesn't mean that the parent curve converges. But if the parent curve converges, any embedded sequence must converge to the same thing. Right? So that's just an important distinction there. So the idea is that if we start with our sequence, we convert to the parent function, and if we can take the limit of the parent function and get a number, then that must also be the limit of the sequence.
It's coming.
Let's go. We'll take our break. The place that we left off, we were just we're sort of getting back into sequences, and so we want to take limits of sequences. That's really the only thing we do with sequences is take their limits. And when we talk about the limit of a sequence, we always mean the limit at infinity. Right, with sequences, when we're talking about sequences in series, we're always talking about the tail, limits at infinity. So we're not going to be looking at anything else. So as you look at all these properties here, it's always as n goes to infinity. And these are all super intuitive properties. If you have two sequences and they both converge, if you add them together, that new sequence converges to the sum of what the original limits were. Okay? So the way we sort of say this is the limit of a sum is a sum of limits. The limit of a constant times a sequence is the constant times the limit of the sequence. You can factor constants out, just like derivatives and integrals. A product of sequences converges to the product of limits. So two sequences multiplied together, find the limit of each, multiply them together. And same with division, as long as you're not dividing by 0. So super intuitive, the way you can combine different sequences. Then just sort of some intuition here. The limit of a sequence is based on the tail. If you chop off the first chunk, the leading terms, doesn't matter, it doesn't change the limit of the sequence. But, where is it saying here? So the initial, so they're just saying down here that sometimes they don't even tell you whether it starts at 1 or 0, it doesn't matter, because if you chop off the first 100 terms, it doesn't change the limit. When we get to series, we want to point out, I'll just mention it now, with a series, the leading terms in a series are going to give you a better idea of what the series is going to converge to. Because when we're talking about a series, the tail is basically 0, and it's front loaded, right? A series is front loaded. We imagine the terms going down, and so we're adding all these terms. The bigger terms are at the front usually. So the value of a series is usually more based on the first handful of terms versus the limit of a sequence is based on the tail. So we'll see that as we do more series analysis. Okay, so this section's all about taking limits of sequences. There are techniques that you learned in Calc 1 that apply here. If you wanted to, you could do L'Hopital's rule here and take 12 derivatives if you wanted to, but we have a better way. We have a much better way. So what we frequently do is divide by the dominant term. So if you look in here, the dominant term, the highest power of n is n to the 12. And so you can do division. If you divide every single term by n to the 12, you will have something equivalent. So you could end up with this. So if you divide by n to the 12, if you divide by that highest power of n, you've got that. And remember, you're dividing everything by it. And if you're dividing everything by the highest power of n, that's like multiplying by 1. It's the same idea. If you're dividing the numerator by n to the 12, you're dividing the denominator by n to the 12, that's essentially multiplying by 1. Now we can solve this. This is done by inspection here. Where does this little fraction go to?
0.
That goes to 0 because its denominator goes to infinity. Its numerator is constant. So the overall limit is
1/3.
1/3. Yeah.
Can you do the thing with like, if it's the same exponents, just divide?
So in college algebra and pre-calc, when you're talking about limits at infinity for a rational function, if the powers match, you take the ratio of coefficients. Exactly. And so that's what's happening. And this is why that technique works. Because if the powers match and you divide out the power, anything with a lower power is going to go to 0, and you're going to be left with the quotient of leading coefficients. That's why that strategy works. Okay, so let's look at this one. Here we see the highest power of n is n to the 5th. You generally have two choices. Sometimes you're going to hear people say divide by the highest power, and other times you're going to hear divide by the highest power in the denominator. Both are going to get you there. Let's take a look at both. So here, let's divide by the n to the 5th first and compare it to what happens if we divide by n to the 3rd. So if we divide everything by n to the 5th, so everything is being divided and simplified by n to the 5th. So does everybody agree with that? So divide this by n to the 5th and we get 1. Divide that by n to the 5th, 1n cancels. Divide that by n to the 5th, 3 n's cancel. Divide that by n to the 5th, 1n cancels. And so here we have that going to 0. This whole denominator is going to 0, correct?
Yes.
And is it going to 0 through positive numbers or through negative numbers? Positives, because when we think of n is going from 1 to infinity. You can chop off the leading terms, doesn't matter. So n is definitely positive. And so the denominator is always positive. So what are we going to say this limit is equal to then?
Positive infinity.
Positive infinity. So the numerator is going to 1. The denominator is going to 0. Right? So we're thinking about divide by 0.1, divide by 0.01, divide by 0.001. So that's exploding, going to infinity. But everything's positive, so it has to be positive infinity. All right, arctan of n. So this one, the limit of arctan of n, that's going to be the same as the limit of arctan of x as x goes to infinity. So we can think of the arctan function and the arctan sequence as being embedded within the arctan function. So we know that the arctan function looks like that with a horizontal asymptote where?
Negative 1.
Oh, pi halves.
Pi halves and negative pi halves. Right, that's what the arctan function looks like. The arctan continuous function. And so our sequence that starts at 1, arctan of 1 is somewhere over here, pi over 4, and here is the embedded sequence. So that embedded sequence, the discrete arctan, is part of the continuous arctan, so the discrete arctan limit is the same as the limit of the continuous arctan, which is pi over 2. So that'll be, so if you can find the limit of the continuous function, it has to be the same limit for the sequence that's embedded within it. Here's a technique that's going to be super important, and if you look at the worksheet, I've got a lot of stuff that, so I released your worksheets. Everything should be caught up. So worksheet due on the 11th, there's going to be a lot of this limit of sequence stuff that is going to be super important that's related to E. So this most likely will be reminding you of the very first time you saw E in college algebra. College algebra, they just showed you graphically. And the way that we do it in Calc 1 is with this log limit process. So we'll do the log limit process as a reminder. But let's just take a quick sidestep back to college algebra for a minute. And so what you did in college algebra, you had this function, they called it a function. And the question was, well, what's the limit of that function at infinity? As x goes to infinity, what happens here? And hopefully, you sort of did this kind of thing in college algebra where you said, oh, well, if the base is less than 1, this is going to approach 0. Right? It's going to have a horizontal asymptote at the x-axis. And if the base is bigger than 1, it approaches infinity. And so that's kind of the setup. It's like, okay, we now understand this in college algebra, that if we have a proper fraction and multiply by itself, it goes to 0. If it's bigger than 1, it's going to go to infinity. When you look at this, you're saying to yourself, well, sheesh, that's always bigger than 0.
It's always bigger than 1.
Which is bigger than 0.
It is always
So-
bigger than 0. It's always bigger than 1. And that's
So it's
the point.
always bigger than 1. So it's always bigger than 1. So most of us, when you first see that, you're like, oh, it's got to go to infinity. If the base is always bigger than 1, and any time you have a base bigger than 1, that limit is infinity, it feels like that should go to infinity. But what they show graphically in college algebra is that no, this goes to E. So it's an indeterminate form. The indeterminate form is 1 to infinity. So 1 to infinity, in Calc 1, you'll call that indeterminate. Why is it indeterminate? Because you can have this form, and you can have sometimes it goes to infinity, sometimes it goes to 1, sometimes it goes to something in between. This one goes to E. So super important limit. And the idea is that 1 over x goes to 0 fast enough for this limit not to explode to infinity with that exponent. 1 over x going to 0, usually we think of it as going to 0 fairly slowly, but in this case, that's fast enough for this indeterminate form to actually have a finite limit. And then you'll look at this in general. In general, you can sort of generalize this, and this is what the worksheet's all about, to remind you and get you some practice. If you have something like this where that's an A, and this is a B up here, so you have coefficients, this is going to end up going to E to the AB. Now in the exam, you're going to be asked to do one of these with the log limit process. It's going to be important, I think it's important, that you sort of have this piece memorized because it's super helpful. But you will have to do a log limit process on the exam. So here's how we prove these things. So we first come over here, and you can use n's or you can use x's. My habit is always to go to x's because I know I'm going to differentiate, but you don't have to use x's. You could use n's, that's totally fine. So the first thing we do is take, we call it y or call it whatever you want. It's a function. And what we're going to do is take the natural log of both sides. And we're going to take the natural log of both sides so that we can pull that exponent down. That allows us to pop the exponent in front. So that x is going to come down in front. And then we have this. And then what we're going to do is take the limit of both sides. So our whole goal is to evaluate the limit of this. So now we're going to take the limit. And on the left-hand side, when we take the limit, that limit can move inside the natural log function. So now we have this. Don't really need parentheses around that. I'm going to pull them off. So now we have that. And our goal is to get all the way down to here, right? That's what we want. Y is what we're going to call the original thing. And we want to know, well, what's the limit of that original thing? So in the very end, what are we going to do to both sides to get rid of the ln?
Multiply by 8.
Yeah, we'll exponentiate. We'll exponentiate both sides so that the e and the natural log will undo each other. Okay, so now on the right, we want to get to this limit here. And to get to that limit, we want to go and try to rearrange it so that it satisfies the hypothesis for L'Hopital's rule. L'Hopital's rule says if we have an infinity over infinity or a 0 over 0, one of those types of indeterminate forms, we can take derivatives. And the concept in your mind should be, if you have a fraction of functions that go to 0 over 0, infinity over infinity, the best approximation for any function is its derivative. So two functions are going to approach the same thing as the two best approximations, right? So if we've got our two functions, and then we take the derivative of the two functions, the quotient of derivatives, the quotient of best approximations, should be the same as the quotient of functions. Should approach the same thing. Otherwise, it's not a very good approximation. So we want to try to get this in L'Hopital's form. And to do that, what we know is that this natural log piece of it, what does that go to as x goes to infinity? What does the whole numerator go to?
Oh, 1.
Oh, 0.
0. The inside goes to 1, using what Robert suggested earlier. These are both linear, so the powers match, so the limit is the quotient of coefficients. Coefficient there is 1, coefficient there is 1, and then the natural log of 1 is 0. Okay, now this x, the way we handle that x is to move it into the denominator. If we move that x into the denominator, it becomes a 1 over x. Right? Division by 1 over x is the same thing as multiplication by x. Everybody agree with that? Multiplying by 2 is the same as dividing by 1/2. Same thing. Multiplying by 2, dividing by 1/2. Multiplying by x, dividing by 1 over x. Same thing. Now we're in L'Hopital land. So now we can take the derivative of the numerator and the denominator. I'll indicate that just by putting 0 over 0 here on the equal sign. So I'm going to use L'Hopital's rule now. L'Hopital's rule says the quotient of functions approaches the same thing as the quotient of derivatives. So we take the derivative. Let's do the bottom first because that's easier. So that's x to the negative 1, so that's negative x to the negative 2. Everyone agree with that? X to the negative 1, we bring the negative down, so it's negative 1 x to the negative 2, so negative 1 over x squared if we write it without negative exponents. The derivative of a logarithm, 1 over the inside, in other words, the reciprocal of the inside, 1 over the inside, so 1 over the inside, that's the reciprocal of the inside, multiplied by the derivative of the inside, the chain rule. So now we want to multiply by the derivative of this quotient. Now we need the quotient rule. This is Calc 2. all trig, all algebra, all calc 1 mashed together. So quotient rule, the quotient rule says we do low, D high, low D high, denominator times derivative numerator, low D high minus high D low. Obviously, you don't have to put the multiplication by 1, but I find that it's very helpful to just keep track. All divided by low squared. So there's the quotient rule. Now we can simplify a lot of stuff here. So we're going to have a limit. Let's just leave this front stuff alone. This x plus 5 over x. I'm going to leave that alone. We're going to flip this in a minute. We'll get to this denominator in one moment. Let's just simplify what's up here. So we're multiplying by 1. So really all we have is x plus 5 minus x. X plus 5 minus x is just going to reduce down to 5. So 5 divided by x plus 5 quantity squared. And then we're dividing by a fraction, so we multiply by its reciprocal. So if we multiply by its reciprocal, we are going to have negative x squared divided by 1. Obviously, you don't need to write the division by 1, but we will. Okay, so now we're going to have limit. Let's cancel the x plus 5s right there and cancel 1x. So we have a negative 5x up top and 1x plus 5 down below. So one of these x plus 5s went away, turned that into a 1. One of these x's went away. Everyone okay with that? And then what is that limit?
-5.
Negative 5. So again, Robert's rule. He suggested if we have the powers matching, we just grab the leading coefficients. Or, technically, we could, if we wanted to do more math, you divide everything by x. Let's just write that step out just in case that's not 100% clear to everybody. So if you divide by that highest power of x, you would end up with this limit as x goes to infinity. And that little fraction there is going to go to 0. So this overall limit is -5. So at this stage, we have an equation. On the left, let's write it out a little more formally. So right now we have natural log of limit of y equals -5. So that's where we're at right now. And the whole goal is to find limit y, the limit of y. Y is what we started with. This thing up here is y. So we want the limit of that. So what do we do to both sides? Exponentiate. We exponentiate both sides. So we put in e as a base for both sides. That is going to lead us to limit of y equals e to the -5. So that is our limit, e to the -5. Capiche? Capiche or casquash?
It works.
Okay, so now I showed you this shortcut over here. This shortcut right here, if we are getting, e to the -5, it feels like, well, can't we do some algebra up here? And the answer is yes, and this is what the worksheet is all about. The first section of the worksheet is being creative with this. Notice that you could do the following. We can't split the fraction right now because the denominator is multi-termed. But we could flip it. This is the same thing as, if we flip this, what would the numerator become? What would the exponent become? -n, right? If you flip, you change the exponent by a sign. And now you could split the fraction, and that will become 1 plus 5 over n to the negative n. And the a value is 5, and the b value, I don't know where that went.
B is negative.
Yep. B is -1, A is 5, so that's going to go e to the -5. You're going to have one that you have to do by hand, though. But these, if you're clever, though, you can check your work really easily. All right, so this one, what's this going to go to?
-4 or e to the negative 4.
E to the -4. Because you can think of this as plus with a minus up there. And so then the A, the capital A is -4, the capital B is 1. So we should get e to the -4. But we're going to do it with our process. So we're going to say y is equal to 1 minus 4 over, I'll use an x out of habit. It's fine if you want to use an n. Then we take the natural log of both sides. We can be efficient here. We're taking the natural log. The whole point is to allow the x superpowers to come down in front. So this is going to be x times natural log of 1 minus 4 over x. And then we take the limit of both sides. And on the left, the reason that we can move this limit to the inside is that limits can pass through continuous functions. Limits pass through continuous functions. For example, so this is the idea that we're using. Lims pass through continuous functions. Like if you take the limit as x goes to 4 of x squared, really what you're doing is passing the limit through the x squared function down to the x. Because the x squared function is continuous, so you can pass through it, and you can always get down to a basic limit if you use your properties. The limit of x as x goes to 4 is 4, and then you square that and you get your 16. So that's the idea. If you have the limit of sine of x as x goes somewhere, you push the limit through sine into the inside. So the limit can always jump through any continuous function. And then over here, we want to, our goal is to get into L'Hopital's hypothesis. So we're going to shove the x into the denominator. And when you shove it into the denominator, it becomes 1 over x. Now, are we in L'Hopital form? Let's see. As x goes to infinity, this is 0, this goes to 0. So certainly we have a 0 there. And what about the numerator? As x goes to infinity, 4 divided by x goes to 0, natural log of 1 is 0, so yeah. We're in L'Hopital land. What time does this class end?
45.
Right now?
Yep.
Oh, okay. So we just finish and we get e to the -4.
Well said.
I'll write up the last few steps here just to finish this one off. Yeah,
Something
I couldn't even remember what time this class